已填色，挤出话筒。
宇航，要问你一个问题吗？也没有就问吧。你觉得在这里上课跟 UM 上课有什么差别？哦，真的？比如说？
我们的 continuous assessment 是一个 test 跟一个 assignment 嘛。
不可能呢。
这
是我们要过 MQA 的哦，这种东西。
不知道我们讲过啦，一个 test 跟一个 assignment，这里是4
哦，一个 assignment。
一个 assignment。
它的 component 来 mark 是跟我们一样吗？assignment 很大，来。
没有20分好，就20分 test， 20分 assignment， 60分 final。
哦，它把 final 变很大。反正我们这边的test 应该是不会超过40哦。谢。但是我们这边呢比较 match 我以前读书的方法哦，我学的也是这样 ，final 不会占到超过一半，除非是那种first year 数学那种 engineering 啊 ，maybe 就会啊，因为他们没有什么 assignment。真奇怪。
知道。认真啊，所以。
OK。
没有
嘞，不是我朋友，我弟弟就是这样好吗？他们来 Hari Raya 前后都是在家上课吧？
他们都还
不是，这样离谱哎！我们要闪接厦门做这件事情。学生会的问题吗？不是老师的问题。
但是要是没有假期，学生会又会去投诉还是什么的？
没有。
去申请假期了。
假期是什么情况？
那怎么干都会的。
什么叫申请假期？回家。是吗？我以为是老师的问题。老师要回家了，我觉得。
学生也会的。
这样好，我们也要回哦。怎么你们不补课？
正
常都不用补吧？
我们学校的才不是好。
正常是不用补课的。
OK。非常新奇。应该也是哦，我们以前同学哪里有补课？
对啊，补课才不正常好吗？
教完就教完啊，为什么还要？
是吗？是啊。
教完再补啦，好累啊。
OK。开心，明白。开心。OK。轻松很多。Okay, let's start. So before returning to homological algebra, we'll continue with a bit more of category theory. So this time around, I think we will reach Yoneda's lemma. Yeah. Okay, so later on you will know what Yoneda's lemma is. So I think we already introduced a category, right? The idea of category. So basically two things you need to specify. Actually, category consists of two data. So one data is objects, and then the other data is morphism. You need to tell me the map between two things here. Okay, so now we're going to introduce function. Okay, function between categories. So let's say you got one category, so you got another category, so maybe this one category 1, number 1, or category A, and then there's a category B, right? Okay, so what's this function here? So we no longer call these things function. We'll call this functor. Okay, why is it functor? Because function is like one input, one output, right? But then category got two things you need to input. So one is objects, the other one is morphism. You need to tell me both things where they go. Okay, so for example, let's say this functor is f. You need to tell me, so let's say objects, so maybe fb. So you need to tell me what's fa and fb. Okay, and then let's say if you have a map between a and b, you have to tell me what is f of f. Okay, you need to tell me like what this map become after this functor, this function between categories. Okay, so basically this is the idea of functor. Okay, makes sense so far. Okay, so we call it functor because you have two different input for this function already. Okay, so we call it functor. Okay, okay, so good. So let's define functor now. Yeah, I will give you a few examples. So let's define it properly. So let C, D be two categories. Okay, so we will define something called covariant functor first. Let me see if I'm gonna do contravariant later. Okay, I will do contravariant later. So I'll do covariant first. Okay, so let's define what's called covariant functor from FC to D. Okay, so what is it? Well, first thing first is the same as function. Okay, any object you need to tell me an assignment. Okay, so assignment of an object f, let's say fc, okay, in the object D, okay, for all c in the object C. Okay, and also you need to tell me function. Okay, so you give me a function from, let's say, C to, let me think, which notation is better. So C to C prime, let's say. Okay, then you need to give me a function from FC to FC. Okay, such that some property you need to hold. Okay, a bit like category definition for morphism. So first thing is, you cannot simply send your morphism. So something is fixed here. You need to send identity map to identity map. Okay, you cannot send it to different places. And the other one is about composition. Okay, so if you have f on two composite, okay, should be the composite of fb false fa. Okay, so this is what we call a covariant functor. Okay. So if you look at this covariant functor, right, it's like following the order. Okay. So the order is you have a map from C to C prime, then you also have a map from FC to FC. And next one, we can turn this direction. We can turn this direction. But if you learn algebraic geometry, right, I think you have seen this example before, or algebraic topology. Okay, given a map, then you can turn the map of the other object.
EC.
What?
EC.
EC, F of EC. Oh, E. I think we usually use identity here, identity map.
Oh.
So this one I didn't specify. You know what am I saying here? Beta, alpha. So alpha is a map from some object to some object, and then beta is the target of this map to other places. Composite of morphism. Okay, is it okay? This beta alpha. Okay. Okay. Then let's give some examples. For example, For example, we could have a functor from ring to group. Can we have this functor here? What sort of functor you can think about? Yeah, forget the ring structure, the multiplication structure, or the, yeah, just forget the multiplication, right? Wait, let me think. Where is the group structure in the ring? Addition, right?
Addition.
Yeah, because ring might not be a field, right? So it cannot be a group structure on every ring for multiplication. So you can forget what? You could forget the multiplication structure. Huh? Okay. In that case, you could so for every then for every ring homomorphism, yeah, from R to X, let's say, how to give a group morphism then? Yeah, so sometimes we say induce. So induces a group homomorphism. Actually, where? Should be from,
就是 R 加去 S 加。
yeah. Why the book say multiplication? Maybe the multiplication. Okay, never mind. I keep this. So the multiplication structure here. Yeah.
Multiplication and
Okay, and then, but then ring is always a billion, right? In the addition part. Yeah. But then I copy cross here. I didn't copy wrong, right? Is it the book use cross or multiplication? Addition. But then I think addition makes sense. Let me think. Yeah. If it's multiplicative, also makes sense now. But then if the ring is not a field, then only identity is in the multiplicative group. Okay. Okay. So from here you can see some sort of functor that you can apply across different categories of. So these are called the forgetful functor. So meaning you forget some of the structures. Okay, for examples, you could have a forgetful functor from group to set, because group, the underlying things is set. We forget the composition. Okay. Well, ring is also the same. I can forget the multiplicative structure, the addition structure. 什么意思呢？日常在用是什么时候？可能当学生忘记的时候，他就在 apply forgetful functor。
那就是
跟他讲积木二我知道里面是什么，把我忘讲什么里面，我忘记了。
还有我在 App 里面有那个
SPN，
就是去那个 scheme 去追，然后来以后那个 space。
只看它的 topology 的 space。OK。Yeah, sure. Yeah. Definitely. Yeah. Your scheme homomorphism 可以like reduce 去topological 的。Okay, and well, like what we did just now, right? Ring, we can just go to, actually more precisely, like we go to the category of abelian group, because the group structure there is abelian. I mean, for addition. And also you can go from abelian group to group. Okay. Forgetting that it's abelian, but still got group structure. Okay. Forgetful here is just say that I don't care lah. The thing is still there, but then I don't care about that property. And then, so from forgetful functor, next one, we can introduce something called a free functor. Actually, this one is something that introduced by you guys before, or maybe Siyu, I guess, in Siyu section. So maybe you can have a set, okay, category of set to free groups. Okay, so meaning you make every set into a group. So, okay, so how to make it a group? Well, you just call every element to be a generator and then use the word to put them side by side. Okay, and then you introduce a new inverse word, a former letter. Yeah. Does it make sense? Okay, so you need to, so let's say your set is like x1, x2, right? Okay, so you need to have like x1 here, s2 here, add in the identity, and then add in the inverse for them, and then so on. Yeah, composite. Make it a free group. Well, another thing is a similar thing you can do in a ring or commutative ring is you make it into a ring of polynomial. Okay, so you also generate by using this elements. So maybe for example, this is just z on x1, x2, or something like that. Okay, then it's commutative already. Okay, so you treat this as a variable and then previously treat it as a generator. So previously, I think the notation looked like this. Similarly, you can make it a vector space. Make it a vector space. And how to make it a vector space? Well, you can write it as your Rn, right? So how do you write your Rn in here? So okay. How do you write your E1, E2? Oh, maybe k times x1 plus k times x2 like that. So can you see like what are their difference? Okay, to see their difference, maybe you need to write down what are the elements here. I write down the elements here already. So here the elements maybe look something like this, right? And then here is the vector form. What's the vector form here? Maybe it's the vector form you can write down here. Maybe something like this. One. So treat this S1, S2 as a standard basis. Okay, so can see from the elements wise, why are they different? Yeah. If you learn algebraic topology, right? So maybe I give you some algebraic topology definition. Maybe you look at pi1. Pi1 from pointed topological space to group. Okay, so meaning I give you a category of topological space, and then you output a group for me. Pi1 is a group. Pi1 of a topological space is a group. So what's pi1 here? Pi1 here is you just, because I have a pointed space, right? So I look at all these loops. So you should convince yourself that if I compose two loops together, right, it's still a loop. And then loop has inverse. How to have inverse? So you can have a direction for loops and then you can go backward. Okay, so you should imagine that I have a loop like this and I can go backward. And then this loop can be from top to 0. Okay, I shouldn't draw this, huh? Is it?
Sure.
I think we did discuss, but need to check.
How many of the machine are there?
But I forget it's covariant or contravariant.
那个 correlation 就是太远了。
Oh yeah, sure. It's a abelianization. Yeah. So if you know that the H1 is a abelianization of pi 1, then H1 will go from top star to groups abelian group. So this one is a pointed particle space. So pointer, it just means that you pick a special pointer. If you learn algebraic geometry before, oh wait, is it contravariant here? Wait, scheme, contravariant or covariant? From commutative ring to set. Is that right? Sounds a bit weird.
你想说虚数吧？
Scheme. You see,
我想表达是虚数，
scheme.
虚数是同样有一直散是。
Wait, let me think. Let me think carefully when I write this. What is this a set? Scheme a set. Okay, maybe reserve this first. Let me reserve this. Let's see what the thing want to say. Okay. Then let me introduce a new category first, and then before I talk about contravariant functor. So for every category, right, we can define a dual category or an opposite category. So something to do with reversing direction, since you see opposite already. So we'll call it a C-op. So we'll define by reversing the arrow. Okay, so here, this is a new category, right? I need to tell you what's the object and morphism. Okay, so object is still the same. Okay, same as the original category, but then the morphism change. Okay, so whenever you want to talk about morphism in C-op from B to A, then this set here is just the same morphism from A to B. Then the definition of covariant functor, contravariant functor, we can define using this. It is a functor from contravariant functor from C to D is a covariant functor from C up to D. Okay, maybe we can unravel this definition a bit. So I mean, object-wise is the same. Okay, you just tell me for every object what this functor have to do to it. But then from the morphism-wise, it's a bit different, right? So let's write down a contravariant functor from C up to D. So meaning if you have the home from C up, home from C up of, let's say, BA. Okay, I should tell you what's the home of D from where to where? From, let's say, this functor is called F. So from FB to FA. But then what is the C up of BA here? This is actually a home of C from A to B. Okay, so meaning I give you a homomorphism from A to B in C. I need to tell you what is from FB to FA. So swap direction. Okay, good. Sure. Can I give any meaningful example here? Okay, maybe I can give you a spectrum example. Maybe we talk a little bit about it. So in many contexts, this kind of functor is called pre-sheaf. Yeah. So pre-sheaf is basically yeah, those are one kind of pre-sheaf, but then that pre-sheaf will satisfy this property, the C-op property. Pre-sheaf. Yeah. In some abstract, algebra paper, maybe they refer this to pre-sheaf. Or pre-sheaf of a set on a category, more precisely. Yeah, pre-sheaf of set on a category. If D is a set, if D is a set. Okay. Usually people call this a pre-sheaf because pre-sheaf will satisfy this property. I mean the pre-sheaf that is coming from algebraic geometry. Okay. Maybe give you one example. At least one. Well, I think last time we say that the spec of R, right? So these are the prime ideal of a commutative ring. Yeah, hopefully you still remember what prime ideal is. Okay, so let phi be a ring homomorphism, okay, between commutative ring. Okay, then so you should think of this as a morphism in the commutative category of commutative rings, right? Okay, so I want to relate to prime ideals. Okay, so then I think hopefully you still remember the correspondent theorem. So the inverse image, okay, of a prime ideal actually is still prime. Okay, so what does this mean here? This means that I give you a prime ideal, okay, in X, you give me a prime ideal in R. Okay, so you can see that this phi inverse here, maybe I call it phi inverse. So phi inverse here give you a map backward. So you can think of this spec as a functor. Okay, so apply this functor to a ring, I get a bunch of prime ideals. Okay. Does it make sense? Okay, and then you can check that this is functorial. Well, functorial means what? Sorry? It's a functor, yeah. Okay. If you learn about algebraic topology, then homology is also cohomology is a contravariant functor. Okay. Let's not write that down. Okay, so far okay. So good. Okay, so a functor, and then you need to know what is a contravariant functor and a covariant functor. And then this is just to say what they did to your function morphism. Whether they change direction or they keep the direction. Covariant functor keep the direction, contravariant functor will swap the direction. And like this, you swap the direction because you look at the inverse image because the image of a prime might not be prime. An image of a prime ideal might not be prime. Okay, so what do we do after function? We talk about property of function, right? Injective, surjective, so on, right? Monomorphism, right? So functor also has similar idea. but we won't call it injective or surjective. So because you need to say about object itself and the function, right? What it do to the function. So actually we will just describe it as a function first. Okay, so we care more about what does this functor did to function. Okay, so we said that a functor is faithful, or another term, not another term, but another property is called full if fully faithful. Fully faithful is combining these two properties. Okay, so one is faithful, one is full. If you look at the morphism map, so meaning so in this case it's about covariant functor because I keep this direction the same. Okay, so this particular function here is, if it is faithful, this function have to be injective. If it is full, then this function has to be surjective. Okay, so meaning you are injective on the morphism, okay, or surjective on the morphism. Then I will say that this functor is faithful or full. Okay, let's say if you can reach every element in D, okay, that's what we call essentially surjective. Should I define it now? I'm not sure when I'm gonna define it. Maybe I could define it. There's only 3 property that about this functor here. So we will say that a functor f from C to D is essentially faithful. Essentially surjective if for every object D in D, there exists a C in C for every, such that SC equal to B. Okay, I don't know why they don't have injectivity.
It makes sense to talk about injecting.
This one equal, huh? Yeah. But I mean, like, there's no like injectivity on objects, though. I'm not sure why. Why? Does it make sense to talk about injectivity on the object? Could it be because of isomorphism? Okay, I'm not sure. But then if we put these 3 properties together, right? Later, when we define on the equivalence of categories, right? These 3 properties is enough to capture the equivalence between categories. Okay. So, yeah. So later we'll talk about that. Yeah, so far we just need these 3 properties. Okay. So yeah, soon we will talk about already actually. Yeah, soon we will talk about. Well, another idea is about subcategory. So what do you think a subcategory have to be? A subgroup, subgroup to group. What do you think? What does a subcategory have to satisfy? You devise your own definition. First of all, how about objects? Right, let's say subcategory of category. So what's the object? What's the morphism? Yeah, okay. We won't use subset because the reason why we go to category is the collection of object might not be a set anymore. So we'll use a word class. Okay, so it's a subclass. But I still use this notation. Sorry. I still use this notation here. 不是个 set? Category of set. Set of all set. Okay. Right. So I still use this notation, although this is not a subset. Maybe I write here subclass. Okay. How about morphism? Same, same. Okay, nothing special. So the homomorphism that you have in your subcategory should be a subclass of your C. Otherwise, it will be a different category. You won't call it sub if you put more things inside here. It's a different thing. Right? It's sub meaning it must be a sub collection. Obviously, it has to be closed under composition, identity, and so on. The property of category you need to. Okay, so but then there's a possibilities. We will call that the subcategory is full. It is full if the home in your subcategory is exactly the same as the home in your original category. You can imagine a case that I can pick less, then it's not full. If it is a full subcategory, then the home space in your subcategory have to be the same home space you get from the original category. Does it make sense? Because in principle, you can take less morphism here. But then if they turn out to be the same, this is a full subcategory. Okay. Good. It is full if 这个东西发生。或者说这个 how is full. This subcategory is full if their home space is the same for all elements.
什么情况下只是一个 subset？
什么情况下？
就什么时候、什么情况下它的 home space 只是一个 subset？
Well, I mean, like 随便就是你自己决定啊，你可以 pick and choose 不是？
比如说 category of public group 是 category of group 的一个 subset。
哦，你要问这个问题，你要敷的还是不敷？不敷啊。Abelian category of abelian group is full because 那边可以 define 的 homomorphism 肯定是从 group homomorphism 来，所以那边是 full 的。
它有不符的，
你说天然的例子还是不天然的？
有天然的。
有没有天然的？就什么情况是你上不了个原本的 homomorphism，原本的 morphism 是不能问的。通常原本那个是最多条件那个咯，除非你上的时候是。I mean 不天然的，就是你任意丢掉一些 homomorphism，对不对？天然的，天然应该是大部分，一点大部分不符，有没有天然的？I mean based on 我们讨论的东西，based on 我们所懂的 category。哦，有啊。如果从 set 去到 group 的话，从 set 去到 group 的话，不一定每一个 set function 是个 group homomorphism，那就不符合。So for example, category of group is not a full subcategory of a category of set。不一定嘛，可能每个 set function 都是一个 group homomorphism。懂吗？ Maybe find an example here. So for examples, the category is not O sub 3 of set. Okay, not all set function, set-wise function is a每一个 group homomorphism 肯定是个 set-wise 的 and then 每一个 group 都是一个 set. Right. Okay. Yeah, in that case, I think it's more general. Yes. 不符的东西了。Okay. Then we'll talk about equivalence of categories. This is what function can do to you, right? Okay, if you can do a mapping and then you hope this map can tell you whether this two thing is the same or not. Okay, like bijection, are they having the same number or not? Or homeomorphism, whether the open set correspond to each other or not? Or vector space isomorphism, so whether these two vector space has the same dimension or not. Okay, so now we're going to define equivalence of categories. Okay, so when can we say that two categories are the same? So we'll say that a covariant functor is an equivalence of categories. If three things. If it is full, or sometimes we call fully faithful, if I combine with faithful. Second, faithful. Third is essentially subjective. Okay, so this do a little bit more than the function thing. For the function, right, you just care about injective and subjective. Okay, but now you should think about like this full and faithful only do set condition on the home set, but then the objects, you reach everything in the objects. Okay, so this covered by essential subjective here. Okay, so maybe you might feel weird here. Why not? Can I define a F inverse? Okay, it's like your previous suggestion. I mean, like bijection, right? You can define inverse. So, does there have an inverse or not? So, in this case here, in the case of category, right, you should remember that you need to care about the function at the same time. Okay, when you want to define functor. Okay, so to make all these things work, right, we need another higher level of map, which we call natural transformation. And later we'll talk about it.
GPT 跟我说 fully faithful 已经考了 essential objective 解释。
没有可能吧？没有可能
啊？
没有可能吧？没有可能，我从来没有看过。How come？你私下跟他讲没有，看到他回你。Okay. So before we go to the another formulation of this definition here, maybe we can talk about limit first. Okay, because it's about functor, so we will stay on functor topic a little bit longer before we talk about natural transformation. Okay, which is something between functor. Yes. 啊，什么问题？什么问题？什么问题？ Category of category. Category of category. 想一下这句话什么意思？
对吧？
它的 object 是 category，
它的 object 是
homomorphism 是。应该有吧？我在想它这个有没有特别的名字啊？
就是你提我只是随便想好了问题。
There's one thing called functor category. Let me think. Functor category is object is functor. And but then for that, I need to fix two category, I guess. But then now you are not fixing. 应该有吧 category of category. I'll try and write that down later. Okay. Good. Okay. So let's dwell on functor a bit longer before we talk about map between functor. By the way, I think all these things, right, is still in Alufi. But then if you like to read more, you can go to the Tom, if I don't spell the name wrong, I think Tom Lanster. What's the topics? Is it something on category theory? Or there's another book I like also. I think it's by Emily Real. Also on category theory. I think this is category theory in context. So I guess the first place that have this category theory is a paper written by what's the name? I forgot the name. There's a paper written by I recall the name. So before Grothendieck using it, I think there are people already define these things. It's just that Grothendieck already use this language to expand the subject of algebraic geometry. Yeah. Oh, I think okay. I think the paper is written by Sunday McLean. Sunday McLean. Yeah. Okay. This person, okay, very important. Category.这个图片 category。
你想，它不仅有模数子，还有模数这个模数的一个是一个投进去。
我连我现在在了解那个 object 是 category 的概念是什么？
这个 set 是它的一个 object，然后 category。
对，没错。
但是我觉得它不能是因为 category of different 好的是看到四十
啊？有没有 category of all category？应该是可以接受吧？在 category 里面。啊？
没有 category。
他讲什么对吧？
这个是它的 for the same reason you have a set of poles。就
什么 reason 呢？
你知道这个东西会 for set of poles。它的一个那个条 small category。对。
small category 的意思就是说那个 category 的 home space 是一个 set。I think。什么 reason 呢？什么 reason？I thought 那个 reason 已经被 class 解决掉了。
它能够扯到 cross 的 behavior students。
为什么？我以为那个 class 的那个字已经解决掉那个问题了。所以他意思说他可以接受 class of all class 啊，我的意思说。我不懂，我觉得是这样，我不懂。Yeah. Okay, so this person, okay, very important person. I think I think this person is doing infinity category. Okay, so that's why each can talk about two categories, right? So there's something called infinity category. Hopefully, this is the real framework of our mathematical foundation. Hopefully, one day. Maybe this will be more important than set theory one day. Okay.
我觉得确实 fully faithful 可以推导出 object 上的 object，对不对？
不可能吧
然后我就跟你看见了，
？Seriously？不太可能吧？不可能。你只是在 morphism 上面东西，怎么可以推导出在 object 上面的东西？
因为 object 你本来就不 object 的相问题，就它这边只是说 isomorphic。
哦，isomorphic 哦，对，哦，对耶，这个是 isomorphic，here is isomorphic，not necessarily equal. I think this is the art of category theory. So in category theory, right, seldom we care about equal. Let me change this. 好像我那时候写到等于句，这个 OK，but then，难道你要 apply identity？可能不可能，我觉得不可能。等下我们再讨论，but then 我觉得不可能。OK， so let's continue. So let's say we have a covariant functor. Okay, we're gonna define a limit. Okay, so not the calculus kind of limit. Although this semester I was teaching analysis. A different limit here of this functor here. Well, if you look at the Tom's category theory, right, they will have more precise condition on this category I here, but then we try not to put too many technicality here. So what do you need to remember is the limit of f is some object, okay, in the target space, such that whenever if you have a morphism, okay, morphism from where to where? From L, from this limit here to some object met by this F here, okay, because these two land in the same target space, right? Okay. I is some object inside the category I. Okay, so for all I in check I. So satisfying the following property. First, if you have a morphism from I to J in I, then you have the following commutative diagram. So meaning, because alpha is a map from I to J, right? So because F is a functor, right? So we will have a map from Fi to Fj. Okay, so this is given by your functor. Then we want this to commute. This two map to commute with this map by your functor. Okay, so in other words, lambda j equals to F. Okay, so limit, so meaning what? Limit is not just one object. It have to be object together with this kind of morphism. Okay? That mapping out from your limit. Okay. So it's a bit different. It's maybe a bit different from how you think about a limit in analysis. Limit analysis should be something that you want to go reach, right? Okay, so now it's someone that you go up. Okay, but then later you will see why is it like going in. But now it's like going out like for now only. Okay, for now it's like going out. But then now I will let you see why is it going in. Okay, the second property. That is what is going in. Still remember universal property about going in. One is out, one is in. A unique map that going in and going out. Do you still remember? If there's a map that's uniquely going out, what's that object? If you have an object, initial, right? You going in like going out uniquely. Going in uniquely is final. This thing is a final object. So that's why we call it a limit. Okay, so we'll say that this L is final such that if M is another object that come with the similar property. So it has the morphism as well. Let's call it mu I. I guess satisfying the previous requirement. Then there will exist a morphism from M to L, making all the relevant diagram commutative. Okay, maybe we can try and draw this out. Okay, so previously you have Fi to Fj, right? Okay, F alpha here like that, and then lambda I, lambda J, then lambda L, right? So maybe you have another M that go in, right? So M maybe go in here, maybe go in. So then there's a final map. Here is M mu I, and then mu J. Does this look familiar to you? Does this look familiar to you? I mean, in a very early class. But what kind of final object that can stick inside here? Look familiar? Does it look familiar? No, huh? Something fox or what? Cannot recall. Cannot recall. Cannot recall. Either product or direct sum. Which one? Cannot recall. Product. Okay. So you can think of this as like generalization of those things. Okay, I think I will mention a little bit. I'll mention some of them. Okay, I think I'll mention some of them. Okay, in fact, most of the things that you learned before can be phrased in this limit language here. Okay. Let me see. There's some remark here. Usually we call this a con. Okay, usually we call this a con, and then this limit here is a universal con, such that everyone has a map. It is a final object in the category of con. And then this limit here, not surprisingly, is unique up to isomorphism only. Actually, we will have this notation. So maybe write this. So this L here, sometimes we write it as the limit of F. Okay, and then there's a left pointing direction, reminding us that L stands before all objects of C. Okay, so it stands before. 他说他 stand before so before 讲他呢，因为他在往前走 stand before 全部在左边，没有那个 L 在左边，L 在左边，L 在上面咯。哦 ，OK， okay. Yeah. If I draw like this, then you should estimate I should have another thing that is going right. Okay, later we'll define that, which is a con limit. Sometimes we call this an inverse limit because it goes the other way. Or projective limit. Co-limit. No. This is called inverse limit also. Yeah. This is called inverse limit. Because usually limit go the positive direction, right? Or positive orientation. So this one go backwards. So the limit here is the inverse limit. No, not quite also, right? Because if this direction is correct, you are the final thing. So you are reaching the final
就是那个时候大概跟你的有关系。
啊，有啊，有啊。I think direct limit is the co-limit. Direct limit is co-limit. And this is the inverse limit. So you should expect co-limit is the initial thing. Direct limit is a initial thing. Huh? Offset factor 不明白。
它好像是做一个 offset 的，这个你这个会考。
没有，你的应该是在 fix 那个 i 吧？我觉得你应该是在 fix 这个 i，你在 fix 这个 i，你在 fix 这个形状。
哦。
Yeah， 你在 fix 的是那个形状。Okay, so since we talk about this, okay, maybe we take a break. We'll come back for example for limit where if we take a different I here, what kind of limit you can get? Okay, if I change this I, what sort of limit you can get?
这个离能把我们熟悉的未来的4次。
Can we do that? Then you need to figure out what's this category I first. Cannot. Okay. I think it's worth to think about it. Let's break until 309.
So 你如果想要 prove f(x) isomorphic to f(y) implies x equals to y， 然后这样子的话，你有assume 这个，那么既然它 full 就会有 f(x) 去到 y 是的 ff 等于 phi，应该它 faithful 可以 implies 这个东西是 invertible。对啊，可以。
这个 OK，然后又因为 phi 是可逆的，
因为它是 isomorphism。
我只拿到这个 map 吗？Then 我怎么知道 f 是可逆的呢？
我觉得是再用一次 for，因为你 inverse 也会有一个东西送到它的 inverse 进去。
来看我上个厕所。
行。 聚在一起，这怎么让那个插头变高？哇，我们插头变高了，我们是我们是多少？这个高，可以这么说啊。主要是一开始提前开的是有包括那种小小的部分，就是反射上不去的，所以它调整过后，我们的插头比这个更高，怎么样高？主要还是它那个调整，因为我们其实调整不到东西，我们一开始也是大概10多瓦的，因为达到那些很恐怖的也被查成查到，就他怎么调？也问他，他上次讲啊，他就把那些小的部分的东西就关掉，包括你们之前的这个，他那个 reference 分离的时候也放屁，是啊，就是他查重率很高嘛，他的这边更高。因为我很多东西都是直接这个希望他说的 definition，也不可能自己改掉。对啊，他先帮自己改，我就在想，你到底那个怎么做？对对，高不高？我跟那个谁，其他的也是高。然后那时候我们能调的也就说了7、8千也是没有用。对啊，到最后也是他从系统上调整的，我们能说。那现在系统更新了，他也没调。不知道，应该可以。那我问他的时候，因为我说我还问你这个人太过分了。然后呢，回答批评，你给我记掉了。你看是不是那个 injective 可以从 fully face 退出来？写给你啊，我写给你了。再次。
F 是创业 S 去 Y 了，
这个是从 X 去 Y，那这个可以，这个不是可以 vertical 吗？那直接就可以从 Y 去 X。对啊，这个是 isomorphism 的意思就是存在一个泛 inverse 从 F1 去的 Fx。那我要让我的 FF 等于100，然后 F 值等于泛 inverse，因为我的Functor 是5。然后这样子的话，我 F compose G 就是 FF compose FG，就是 phi compose phi inverse 就是 ID，就是 FID。所以通过 Facebook 可以得出我的 F compose G 就是 ID，然后 G compose F 也是 ID。然后这两个东西都是 ID 的，那么相当于是 X 跟 Y 是 isomorphism。
但是我要 f of 一个东西的对面的一个东西，f of 一个东西的对面。
Injective 的意思不是 Fx isomorphic 和 Fy implies X equal isomorphic F1。Injective 往这样子。
我要每一个 D 的东西是一个 X 来哦，
你会每个 D 的问题
来是每个 D 是 FC 或3C 啊。
那个不是 sensitive 吗？
对啊，那个是 essentially 是的。对。
我只是在跟你解释为什么没有 essentially injective。
为什么没有？
为什么我不用 essentially injective？
你是在讲这个？OK，是。
对，是一共是 FRP 是你那边调的。
我调，2是调
让你听。反正你们两个都有调这个。你一开始给我们是我们全部的大多数人都很高啊。
对。
然后你过后关掉什么东西，我不懂的。
这样是那个 RC， 应该是减少的什么几%以下的东西。
就是把那些
RC 调。
虽然是涨是吧？
它会自动帮你把。你跟他讲，大部分都是在备份，所以好吧。因为你出来的东西应该都是那种小于几%的东西。
对吗？好吧。
嗯？啊？你有漏吗？上次？
对，我那时候教这个星期还已经在那个系统里面的，然后我再教就显示我自己。
哦，那个180的那个。
对。
哦，你是讲的 essentially injective，我一直想奇怪，也是讲 subjective 那个。OK，你们全部有在听你们在讨论没有？我还在解释为什么没有 essentially 是 injective 这件事情，就是你只要有复利非复，它就会 essentially 是 injective on 那个 on object 啊 object yeah object yeah basically 你用复的条件把它拉回去morphism between x y and then 你用非复 to say that 里面的 composite side and then identity equals to f identity 这个是那个方的 property。我觉得很奇怪啊，就不会给就 essentially subjective，原来也是讨论那个 injective。OK，but then 我们还有一个问题要解决，不是 category of all category 这东西。下次看一下，好，下次来说，我也没有什么好 comment 的现在。OK，well， so let's look at different eye. Let's look at different eye and then see what we get actually. Okay, so let's look at a very simple eye. Let's look at a very simple eye. Well, this eye is just consist of two things. So let's say 1, 2. If you want to put two dots also can, never mind. And then with identity morphism, so meaning you only have map between 1 and then map between 2. There's no map between 1 and 2. Okay, so if you want to draw this cone, right? So you only need to put your L to this 2. Huh? 什么？ I is a category, yeah. So I abuse notation from set. Okay, so what's the map? That map. Okay, so what's the limit of a function? Okay, that map out from this I here. Okay, so what do you think? Okay, such that if you have another M that map into here, it will commute, and then there exists a unique map here. I think this one look more familiar. Anything? Okay, so this thing should be something called the product. Did we define product in a general category? Did we? I define one or any one of you? Me? Did I did that in general category? Okay, let me check. Kind of forgot already. Too long ago. Because sometimes we switch from category and then we switch to group. Let's see. We define. Oh, sorry, I searched the wrong document. So we define product for set. Product for set is a final object. Okay, product of set is a final object. Okay, so in general, it should be a final object. So we generalize it. Oh, then become core product already. Oh, okay. I think counted as here. Here, this one. Okay, we generalize this idea of product in any category. Okay, such as a final objects. Okay, in this category of Fox, let's see. Okay, so you can think of this Fox category as the discrete category with two things. Okay, and then this Fox here will be given by the functor. I mean, given by the limit, in some sense, because the limit have to come with a map into your category. Then there's no map in between these two objects. Okay. So if this final object exists, it should be the product that we define. Okay, it should be product if it exists. Okay, if you have a product exists in this category, it should be called the product because we define it to be the final object of this picture. Yeah. Okay, make sense? Okay. Okay, so let's do a little bit more complicated. How about this? How about the empty category? Sorry, empty functor. Sorry. About empty functor, yeah. Empty category. So what does this mean here? This means that your L should be something that map into, let's say, f of 5. What's f of 5? Anything here? There's nothing here. There's nothing there. It's empty, right? Nothing for you to map on. So meaning what? Is a unique thing that map into your limit. What is that? Unique map that map into here. For any M, there's unique map that map into this. Because there's nothing going out already, because yeah, it's a terminal or final order.
So you can think unique.
Up to isomorphism. Okay. In category theory, usually we don't care about equal one. Only care about isomorphism. Okay, so it's terminal or final. Yeah. Okay, because there's no map up already because it's empty. So I is nothing for you to map. But then the uniqueness you say because okay. So you see, terminal object can be rephrased as a limit. Alright, so limit is a more general thing. Okay, we will see maybe two more examples. So how about this example then? Let's make our I a bit more complicated. So other than these two objects, right? Then you have these two maps also. Fine, better. Okay, so what's this thing here? So well. So the limit of such functor, right? Let me write down this. So let's say this is the F1, this is F2, this is F of F beta, and then here is maybe 我看一下，难怪我下面反的 ，OK， 放它，可以吗？可以，好。So then we have this lambda, let's say lambda 1, this is lambda 2, right? Okay, so this limit here is what we call the equalizer. Okay, so maybe you might think that, oh, what are we equaling here? Okay, what are we equaling here? So is it clear from here? Maybe not so clear from here, huh? Maybe not so clear from here. But if we take beta equals 0, okay, we take beta equals 0. Actually, this thing is what we call a kernel of alpha. Let's think about this. 0 map. If we take beta to be a 0 map, then this equalizer is a kernel. So let's think about it. Why true? Let's think about it. Sorry, here should be beta. Okay. Can we think about this? Why is it true? Okay, so if you write down this equation here, right, this commutative diagram, right, what did you get? So you get that you get f alpha on lambda 1 here should be equal to lambda 2, right? But then on the other side, what do you get? F beta on lambda 1, you also get lambda 2. Okay, so these two are the same. Okay, but if you got one of them is 0, right? What do you see? If one of them is 0, then you get that this is equal to 0. Huh? Let's say your beta is 0. Right? Or let's say f beta to be 0, more precisely, I guess. Maybe this thing is 0. Okay, you get that this f alpha of lambda 1 is 0. Or lambda 0, lambda 2 is 0. Or not kernel of alpha, actually it's kernel of f alpha. Is this the kernel property or not? You think about it. So if I have an M that factorized to this thing here. So is kernel a final objects? Kernel. Yes, I will reach them. Be true universal property for kernel. We prove for isomorphism. Oh, I don't really dictate so. Never mind. Then we need to check it. Is this true? Let's see. Could be the kernel. Thing here has to be a kernel. Then I think it's not directly. You need to check. Perhaps we need to understand this. But then limit is something that come with this, that commute with this. If this vector is 0, surely this thing has to be 0. Then what is this map here? And then this L come with this map. This L come with this map that has to make this 0. Okay, and then this L is an object inside your category. Okay, so what it should be. Okay, the claim is this thing has to be the kernel of this map. Does it make sense? If it's not, then it has to be isomorphic to the kernel of it. We just care about isomorphism, right? Okay. So maybe I should say that this is isomorphic. Okay. It cannot be something less than the kernel, because otherwise maybe this uniqueness doesn't exist. So it has to contain all the kernel. So it becomes the full kernel. Does it make sense? Well, kernel of the data. S1 是 F kernel of the settlement。这边什么意思？它是一个 target， 它是活在它的 target category 里面。Let's say, my F is going from here to D, right? This is my F, right? So this thing should be live inside the object of D. Okay. So my claim here is if this F beta is 0, right? Then this equalizer here or this limit here should be the kernel of F alpha. Equal here is like isomorphic, okay? But then obviously you can take something smaller than the kernel to make this commute. But then my claim is this map here would not be useful. There won't always have a unique. Or even maybe there is no map. Oh, might not be unique. There will be map. Let me think. Yeah, might not be unique. Yeah. Any question on this one? I think this example is pretty important. Pretty important. That how to understand a kernel as a limit. Okay. Actually, this is also how you think of algebraic geometry. How you think of algebraic geometry? The zero set. The zero set. The zero set is like, for example, I'll give you an example. So let's say your function is like x plus y. Okay, but then you want to equate to 0. So you should think of x plus y is one function and then 0 is another function. So the zero set of this x plus y here is the limit. No? This is the limit. The zero set of x plus y is the limit. So you can think of algebraic variety as a limit. 怎么说？解释一下，就是是这个是category of double 是吧？对 ，and the category of real numbers。对吗？对吗？你可以把 algebraic variety 想成这个，你可以想这两边，这个两边是个 function。One is a zero function, the other is a x plus y function. So x plus y in general, 如果你 方随便 S 跟随便 Y 我可以拿到什么号码都可以拿到。But then I just care about the point where they add up to 0. And this is the y equals to minus x line, the 0 set. Then this is the limit. Yeah. Okay. Okay 吧 Make sense? Okay. Then I guess if you learn differential manifold, then I think you should encounter this. A limit of this diagram here. What do you think? What is it? Something that can commute with this diagram. Such that it's unique, it's a terminal object. This is actually called a pullback. Okay, so the limit of this functor over this I here is called a pullback. Okay, so one exercise you can do is, what if my I looks like this? Is a chain. Okay, so what's the limit here? Maybe you can find it for R module first. Okay, so what's the limit here? What do you call this? Anyone got an idea? What this should be? You might have an idea. 应该是一个很熟的东西。我这边没有答案，所以我也忘记了。你想一下。Something that can 不熟那个东西，应该是 union 吧，还是什么？ So you should think that, let's say I have another map, another element that can map to all these things and commute. That should be a unique map into here, such that all the diagram can commute. 就是某些东西啊，某些东西 such that there's this chain map here. You can think of it f of something, but then yeah, you should know. Yeah. Hey, last week we talking about freeness, right? Free module, right? A module is free if we can write it as a, so let's say over R, as a direct sum of R. So this actually there's no restriction on the index, not infinite. Okay, doesn't matter, not infinite. So it can be in general, but surely for every M in M, right, it should be able to be written as a finite combination. Okay, does it make sense? Does it make sense here? Okay, although you could have infinitely many linearly independent bases, but then whenever you write down an element, right, it should be of a finite linear combination. This is what direct sum means. Okay, or almost. Is that almost? finitely many are non-zero coefficient. Okay, this is what direct sum is. Okay, so it should be finitely. So for every element, you should be written as a finite combination. Okay. Okay, sure. Good. Okay, maybe I will give more hints on this one. Yes. All right. So let's continue. Maybe one proposition worth to try is you can check that a map x to y is monic if and only if the following square is a two-back. Okay, so meaning this have a terminal object properties. Only then your function is monic. Okay. Meaning this thing is a terminal object.啊，这是纯什么？有吗？没有，不是，这个是 algebra 问题。哦，okay, the monic here and the monomorphism is the same, I think. But in some cases, actually, these two are different. So the definition of monic is a bit like f alpha is 0 implies that alpha is 0. In some book, yeah, they define monic and monomorphism differently. And then these two should be equivalent. But then the monic here, I think, is monomorphic. Let me think. I forget I pulled from which book already. Okay, maybe it's worth to see why like f alpha equals 0 implies alpha equals 0 if and only if f alpha equals to f. I think this one you should know, right? Okay, some book prefer monic, so this one is monic. Okay, this one is monomorphic.
Go back these two.
Yeah. I mean, right. Okay. Okay. Next, so then we can define what the co-limit is. Okay, so let's define co-limit is. So the co-limit limit to the right direction f of a functor f from I to C. Okay, again, it's an object. So you could expect that this co-limit here should have arrow swapping, right? Okay, so now we should have morphism from Fi to C. Okay, such that we have this diagram commute. So let's draw this diagram here. So we got Fi, Fj, and then I to j. So let's say this is alpha. So for every alpha from I to j, and then we have this map to C, gamma I, gamma j, and then such that it's initial, right? Initial with this requirement. So meaning, let's say I got another m again, okay, that have this map that commute. So here there should be a unit map going out. Okay. Okay. So the limit direction is referring to this direction. Correct. Previously was this going up, right? And now it's leading to this. Because you are limit of this kind of cone, a different cone here. And then now you are asking for a initial object. Okay, so in this case here, we call it a direct limit or injective limit. Previously it was projective, now it's injective. Okay, so just now we have products, right? So this will define something called a co-product. So, okay, co-product is the initial objects. And then previously we've got equalizer, right? Then in this case here, we're going to define something called co-equalizer. So a specific idea of co-equalizer is the co-kernel. Okay. So you should try and write down what's the I you need to define for those things for co-kernel. So if it is the category of set, right? And I represent a chain of all injective map, right? So what's this? This is an infinite union of set. Infinite union of set. I think previously, is it a union or do you need? Wait, I don't know. Yeah. But for in this case here, if you have a chain of injective map, then this direct product should be a infinite union. Yeah. Infinite union. Maybe just now one is infinite product. Sure. Okay. Then just now we got pull back, right? Now in this case here we have push up. Push up. Should I write push up for you? Okay, let me write push up. So for example, right, if you push this thing up here, okay, if you push this thing out, so maybe you ask for this limit here. So what's the L I should put here? So what's the L I should put here is, let's say I got another M, right, that satisfies this commutative diagram here. So what's the L I can put such that there's a unit map going out? Okay, so the claim here I should put Z direct sum with L. Okay, why? Because I only care, what do I care about? What do I care about? I care about what's the map from Y to M and Z to M. Right? Okay, so this object here will be specified if I know what's the Y, what's the map going up from Y and going up. Then there's a one way to define it. There's only one way to define it. Yeah, because you need to make this diagram clear. Right? Yeah, so basically you need to know what's the map from Z to M. And then if I define L to be this, right, it's obvious that this is what this map shows. Because this map comes with this object. So this is defined by you. This is defined by you. So this is the inclusion. And then if I know what's the map from Z to M, basically determine what's the first component level. And then if I know what's the map from Y to M, then I will determine the second component. And then this will definitely satisfy the 0 to set to this, right? Because the first map is already a 0 map. You compose with 0 map, you always get no vector, for instance. I mean, the 0 is not a problem, right? The problem is this triangle here, and then the other triangle. The 0 triangle doesn't really matter because if you start with 0, then yeah. I mean, you know what I mean. So I mean, this triangle doesn't make much sense. The triangle that you need to care about, I think, is this one and this one. Yeah, these are the non-zero triangle. Okay, and this matches with our property of direct sum. Direct sum is also an initial. Okay, and maybe I can give some idea on algebraic topology. So if you learn Van Kampen theorem, right, there's a pushback idea inside there. Okay, so meaning if you look at this intersection here, okay, so meaning U and V are the open set, open cover for your X. And then you look at this pullback here, push out square here. Then if you apply fundamental group, right, it's still a push out. Okay. If you know about algebraic topology, if not, never mind. Okay. Okay. How good time is it? 3:48. Anything to comment here? Okay, maybe one last thing to comment here. So in general, we'll say that, let's say the co-limit of a functor that's n with z. Okay, so what is it? So in general, you can prove that this co-limit here should be the direct sum of all fi portioned out by some relation. Okay, so what's relation you should portion out here? Well, sorry. So what's the relation you need to portion out here? So you need to portion out those x with f alpha on x such that, sorry, for all, you check for all alpha I to j and all x's in fi. Okay, so you are equating, okay, you are equating all the elements in fi such that whenever you have a map from I to j and then you apply f on it, then you should prove this. Okay, so you are kind of like gluing things in fi with the things in fj. Doing things in fi. Okay, so for example, just now this example, right? Actually you are gluing nothing because your fi, fj are 0, so you are gluing nothing. So that's why nothing get glued. Where you just take direct sum. So if these are non-trivial, right, you are like gluing things together. So that's why there's one example. Right? Oh, I didn't write it down. So if you look at the chain, if you are looking at a chain, so for example, let me write down. So if you are looking at a chain like the one we discussed just now, and then such that these are injective, and then such that these are set, maybe set 1, set 2, set 4, right? Set 3, and then set 2, and then set 1. We claim that the co-limit of this guy, right, should be the union of all this set. The union of all the set. Okay. So actually, these correspond to two ways to think about mathematics. So actually, okay. 哪一个东西？哪一个 correlation? Yeah. Okay, so there's a comment about limit and co-limit using geometry. Okay, using geometry. This is two ways to think about, for example, a sphere. How do you think about a sphere? Maybe from analytic geometry or calculus, you think of a sphere as a sum of x squared equals to 1, for example. So this is what? Actually, this is some function equal to 0. It's a limit way to think about this function. But in differential manifold, how do you think about this function? Or in algebra geometry, how do you think about this function? We cover this sphere as a open, use open cover to cover it. Okay, so meaning algebra topology. So we covered it using the maybe half hemisphere, upper hemisphere, and lower hemisphere, and then they intersect at some cylinder, something like that. This is a co-limit way to think about the sphere. Okay, you take union of things and then you join them at some places. Okay, so this is a two different way to think about an object. Okay, so in the modern way is a co-limit way. Modern mathematics is this one. Okay, no? Yeah, so the equalizer you can think about is this for this one. Let's say x squared is going into r cube, and then you make these two the same, right? So the s here, maybe you can consider it x squared plus y squared plus z squared, and then the other one is just the function 1. You make these two the same. And then co-equalizer, then how do you write it out? So you are like embedding this cylinder, the intersection, into two hemisphere. Okay, and then you map into S2. Right, you put two hemispheres together, but then their intersection is a cylinder. And this one is called, this is an equalizer way, this is a co-equalizer way. You see, this is direction swap, right? You see, the two arrows swap direction. But then the object itself also changed the position. One of them I embed into R3, and I look at some function in R3. But then the other is I study S2 from itself. There's a cylinder moves here. And then this one is I embed S2 into some ambient space, and then I look at the 0 set. So this is a limit way, and then this is a co-limit.
那个 sum of x squared minus y 的一个，
哪个？
就是你上面写的是
这个 maybe n sphere, n dimensional sphere is like this.
那个 thing。
Okay, maybe let's try a bit more. So I have sum across different axes. Okay, makes sense. Okay, so this is a very old way to study geometry because you need to embed into some spaces, ambient space before studying it. But this one is intrinsic. When you study the object itself, it's intrinsic. Co-limit. So co-limit here we study the x2 itself, 那个 sphere 本身，不管它多大多小我都可以。But then this is pretty limited 我只是 study 一种 S2 你可以长这样 ，Why not？我可以换成不同 radius 嘛，对不对？ 反正这个就是 S2 本身，管你是大小它都应该是这样，对吗？真的，管大不管小都可以把它切一半，然后看它的 upper hemisphere、lower hemisphere 这样，也是 OK 啊。我讲 upper hemisphere、lower hemisphere as a piece，可以想象吗？就是好像你一块馅饼啊，这样子盖着那个球而已，有一块饼，然后你插呀，放在你的头上呢，你懂吗？盖住，然后放在下面盖住，变球了，对吧？
左边那个最后那个20
啊，
左边那个最后那个20，
这个哦，这个 real number 吧。OK， 可以吗？Make sense? Okay. So modern maths happens here. Intrinsic. If you learn differential geometry, right, you should learn like two kinds of curvature. One is intrinsic curvature. The other is curvature with the ambient space. Okay, here don't have ambient space 啊，我不用把它放在哪里的，我都可以 study 啊。这个我一定要放在 Euclidean space，我才可以 study。Okay, right. In that case, we'll continue on Friday. Okay, we'll talk about natural transformation. Yes.
以上所